All right, good evening. So, finishing up final part 4 of the lesson 6, or lecture 6 for ENGR 2302 Engineering Dynamics. And this will be part 4 of 4 of this. Normally I don't like recording them in so many pieces, but this was recorded not during lecture, but as I found the time over the last couple days. So, let's get this finished. So the final idea I want to cover for the lesson for Thursday is going to be conservative forces and potential energy under conservative forces. So conservative forces here, let us consider work energy, kinetic energy, potential energy, etc. under conservative forces. So conservative forces, again, are forces that do not result in any loss of energy from the system. Forces that do not result in any loss of energy from the system, that do not result in any lost energy from the system, or any energy loss from the system. From the system, or in other words, let's say I had something like this here. An example would be something like this here. Say I had an x, y, and z axis, x, y, and z, and I had a particle at position A1 and a particle at position A2. And here, let's say this has coordinates x2, y2, and z2, and this has coordinates x1, y1, and, well, let's see, comma, y1, my commas look too much like ones, x1, comma, y1, comma, z1, here. And here, so a particle would move in a certain path from here to here, and there would be, at some location, the particle would be here with a certain coordinate x, y, and z, and there would be a certain force producing this path, or along this path. It doesn't necessarily have to be producing this path. A certain force F producing or applied over this path. And if I look at the work done from 1 to 2, this is the work done on this from 1 to 2 is V, again, the potential energy x1, y1, z1 minus V times, or V of x2, y2, z2. Now, what makes conservative forces is that it doesn't matter which path I take. I can take that path, any path I want, but what is special about conservative paths or conservative forces is they are path independent. They are path independent. The work done by them over a path it doesn't matter. The work that results in a change in potential energy, it does not matter. A good example would be gravity. It doesn't matter what kind of sort of circumlocutus path we take, it's going to be the same. The actual change in potential energy of the particle before and after is going to be the same regardless. Or we can think of this as, if I want to use an integral, the surface integral, or the closed integral f dot dr is going to be 0 here. So basically, for any closed interval, or any force, conservative force on a closed path, actually let me do this like this first, I have them in the wrong order. For any force on conservative force on a closed path, well, the integral of f dr is 0. In other words, if I trace in a complete circle, for example, gravity, if I went up and down, if I came back to where I started, the overall change in potential energy is going to be 0. Then here, so there's that. And that's the basic idea of conservative forces. So the elementary work corresponding to displacement between two neighboring points. If I look at two neighboring points, between two neighboring points, well, it will be du equals v of xyz minus v of x plus dx, f of x plus dx, comma y plus dy, comma z plus dz, or negative dv, this would be the velocity vector here, or sorry, the potential energy here, dv of x, y, and z. So f of x d, in other words, f of x dx plus fy dy plus fz dz is equal to the partial, the negative partial of the partial of v, and this is again potential energy, capital V here. I know my capital V is going to look like lowercase v's, but this is capital V. Capital V is the partial of v with respect to x dx plus the partial of v with respect to y dy plus the partial of v with respect to z dz. Or if we recall from our calculus class, this is simply equal to the force vector for a conservative force will simply be equal to the negative gradient of v. The negative gradient of the potential energy v. The negative gradient of v. And that's the basic idea. And I just wanted to introduce that topic fairly quickly. There are some more, well, actually, let's see. Maybe I'll go through one more bit here, and then I'll call it a night. So, conservation of energy under conservative forces. So let's see how this works. Well, the work of a conservative force, again, here, let's say I had let's look at a pendulum. Let's look at a pendulum. And let's say I had here, let's say I had a series of positions, A1, just a generic position A, A2, another generic position, maybe A prime, and then A. A3. So let me put some geometry on this thing. I'll let the overall height here be L. The overall height be L. And I'll use this A2 as my datum, my 0 point for my potential energy. And here, so let's look at the work of a conservative force. The work of a conservative force the work of a conservative force, well, U from 1 to 2 is going to be equal to the potential energy 1 minus potential energy 2. Or if I connect this to concept of work and energy, if I look at the concept of work and energy, if I connect this back to work and energy, well, I know the U from 1 to 2 is also equal to T2 minus T1, the change in kinetic energy. So it follows then that if I combine these together, that T1 plus V1 equals T2 plus V2. T2 plus V2. Or I can simply say this thing has a total energy E that will be equal to T plus V, the kinetic energy plus the potential energy, which will be a constant. So basically, when a particle is acted upon by conservative force, and that would be E is total mechanical energy. Total mechanical energy. So when acted upon by not an outside force, by a conservative force, the total mechanical energy is constant. Mech energy is constant. So not all forces are conservative, though. So for example, some forces that would not be conservative are things like friction, things like definitely friction is a great example, because you're losing heat from you're losing heat or energy from the system in the form of heat to the environment. So that once that energy has dissipated to heat, it is gone, and we have no way of getting it back. That is a great example of a non-conservative force. Another example of a non-conservative force would be something like air resistance. Again, the same idea as friction. But examples of conservative forces are things like gravity. They're things like gravity is a good example. Something like what else? Gravity, spring forces, some hydraulic forces, many different forces that that directly exchange kinetic energy with potential energy of some sort. Okay, so I think that's going to be a very short part 3. I just wanted to finish up my discussions of energy and get into the work of conservative forces, and that will do it for today, and that will do it for this week. And so on next week, for lecture 7, we'll start up with a discussion of conservation momentum, impulse momentum, etc., continuing on some of the topics we've seen before. This week we've looked at conservation, the laws of conservation of energy, and then next week we'll start on with laws of conservation momentum. So that'll do it for today. Thank you for watching, and as always, thank you.